Hey, so welcome to the screencast on orbit. It's a fascinating topic. Hopefully you'll enjoy it. I certainly do. Okay, so imagine this. Imagine if I took like a cannon and I put it on top of a cliff that was 5 meters tall. Now I chose that number for a reason. So if it was 5 meters tall, remember, horizontal motion doesn't keep you in the air any longer. So I fired this cannon at 5 meters per second. That cannonball would come out and it would travel horizontally at 5 meters per second. If you say h equals 1/2 gt squared, what you'll find out is that it takes 1 second to fall to the ground. So it would travel 5 meters horizontally. Okay, so I pick it up, I put it back in the cannon, keep it the same horizontal position, 5 meters in the air. This time I fire at 10 meters per second. Well, it would still take 1 second to fall to the ground, independence of horizontal and vertical motion, but it would travel 10 meters in that 1 second. Okay, I do it again. I put it back in. This time I shoot it at 20 meters per second. Okay, 4 times faster than the first time. Doesn't matter. I'm still just going to be in the air 1 second and travel, in this case, 20 meters. But now when Isaac Newton thought about this, it occurred to him, like, hang on a second, the world isn't actually flat now, is it? So what would really happen is if I fired it, so if you're only firing it at, say, between 5 meters a second, 20 meters per second, the world might as well be flat. But if you're going to shoot it at, say, 8,000 meters per second, and I chose that number for a reason, then what we find is this. The ball would travel so far horizontally from a 5 meter mountain, okay, that in the 1 second it would take to fall to the ground, so the ground should be here. The curvature of the Earth is such that you're still 5 meters in the air. You didn't get any closer. The Earth sort of fell away from the cannonball, and the cannonball would stay in the air. And so Isaac Newton's like, wait a second, this would explain orbit. And then he drew this picture. I love this picture. It's in his Principia Mathematica that was published in 1687. And this is just a remarkable drawing. So he shows basically, like, people often call this Newton's mountain, and he put it at the North Pole. I'm not sure why, okay? First shot, D, let's see it. They're all shot tangentially, okay? So the second shot has more tangential velocity. It lands at E, a little bit faster, F, a little bit more. It'd make it all the way to the South Pole. Then finally he shows another one goes all the way around, and you could fire this cannon and hit yourself with the same cannonball once it went around the planet. And then he just drew the orbits of planets above there, showing like that's all it is. These planets are simply objects that have enough tangential velocity that they keep missing the Earth as they fall. There's nothing mysterious about it other than the fact that gravity is this action at distance force, which, at the time of Isaac Newton was heresy to say so, but he did figure out that in order to explain orbit, you just have to accept the fact that objects can miss the ground if they go fast enough horizontally. So that, just keep that in mind. So an object that is orbiting is simply falling. So here's another way of conceptualizing it. Let's just say it would take 1 hour to fall from here to the center of the Earth. Okay, and if I just let go of the object, it would just fall to the ground. Okay. But if I gave it enough tangential velocity such that it was traveling fast enough this way that in the amount of time it would take to fall to the center of the Earth, r, it travels that same distance horizontally. So it would go, and now look, it's still the same height above the Earth. It's fallen, it just missed the Earth. So in the 1 hour it take to fall from here to here, it would travel so far in this direction that it'd end up over here, and it would just never get closer to the Earth. Now you might think like, well, then why don't we do this? Like, why don't we put a big cannon on top of Mount Everest and shoot it? And the answer is simply this: because there's drag force. As you encounter air molecules, this cannonball would just become a meteor. It would burn up in the air and it'd fall to the ground. It would lose its tangential velocity. All this negative work would be done, get converted to heat. But if you put things in outer space, there's no, or very few particles to bump into, so there's just no drag force, and that's why things that are in space are able to orbit pretty much forever. We go to outer space not to get away from gravity, because the truth is, at orbital altitude, the gravitational field strength is, is like 9.75 or something. It's still really strong, okay? But there's no air to bump into, and so the reason we go to outer space is to escape from air, but not to get away from gravity. All right, now, in order to mathematically describe orbit, it's simply centripetal force, whereas instead of having tension or normal or friction being my centripetal supplier force, it's gravitation. So recall from our previous screencast that the formula for gravitational force is g, the gravitational constant, little m, that's the mass of the orbiting object, or the mass of one object. The big M, the mass of the Earth. So this is your mass, the mass of the Earth, and r squared, remember, is the distance between the two objects' centers. Okay, and centripetal force is just mv squared over r. So I'm just going to substitute this into here. Now I'm just going to simplify it, and I get v orbit. And v orbit comes down to just root gm over r, where this is the mass of the large gravitational body, like the Earth or the star, whatever, okay? This is when you want to commit to memory. All right? Yeah, you can derive it pretty easily just by combining these two basic equations. All right, these ones you definitely need to memorize. And if you don't want to derive it, you can always just go with this one. I'll probably ask you to derive it on the test because it's just so cool. Okay, so this in particular, at this exact speed, at here, this distance between the centers of the objects and the larger object has this mass, this will provide a circular orbital path. That's what centripetal force means. So let's just think about this. And College Board is going to emphasize this year, they say. So if an object is projected tangentially at distance r above the center of a large gravitational object, so we'll call it a source mass, okay? At velocity v equals root gm over r, then it's going to travel in a circular path. So the gravitational force is going to be such that it keeps it traveling in a circular path, and it would do that forever. All right. So this equation is specific for circular orbit, right? Where you're not getting any higher or any close to or any farther from the central object. However, if you remember Kepler, I don't know if you studied Kepler, if you took astronomy, Johann Kepler had Kepler's laws of motion. One of them is that all planetary objects have elliptical orbits. And it's not that there's something about nature that demands that. It's just that the odds of something having exactly this amount of tangential velocity is really remote. So we find that pretty much every object we look at is going in some kind of an ellipse. It could be very close to a circle, but it's still an ellipse. Now, please pay close attention, because this is something that my students didn't do well with last year, and it's definitely something that College Board says they're going to emphasize this year. I'm going to take a sip of coffee. So this blue circle represents what would happen if I projected the object tangentially at this speed, at v equals root gm over r. But if I shot it less than that, then it would sort of fall out of its circular orbit, right? It didn't have enough to have centripetal motion. And so it fell closer to the planet. As it does, gravity gets stronger, and then it gets weaker. So what we'd find is it would travel in an elliptical path, just like Kepler said. And in this case, this ellipse is completely contained within what would have been the circular orbit at that r. Okay, so they only become they only occupy the same point right here. So they are. I forgot the word I'm looking for. I can't believe it. Anyway, I'm going to move on. Okay, tangentially. Okay, so now what happens is this large mass is going to be at the farther foci. So I have two. Ellipse has two foci. It will be at the farther foci. And the entire ellipse of its path will be contained within the circular orbit. So this red one would be where v is less than root gm over r. And if it's small enough, it'll just smack into the planet, as we'll see in the activity we do. Okay, but what if I project it with more than this much tangential velocity? Well, then what I get is the same. I get an ellipse, but in this case, the circular path is contained completely within the elliptical path of the new one. And so what we find then is that now is going so fast it goes beyond what's a circle, and it ends up doing an ellipse. In this case, the larger mass is at the nearer focus of the ellipse. So this is what we get when v is greater than root gm over r. The circle is what we get when it's equal to gm over r, root gm over r. And what if I shot it even faster? Well, it turns out if you shoot it too fast, this is what happens. So if you shoot it too fast, and that too fast being greater than or equal to 2 gm over r, then we find out, and we'll see why in a later lesson, that the object won't orbit. It becomes basically gravitational unbound. It escapes from the system. It's not that gravity ever stops pulling on it, it's just gravity's never going to be able to make it complete that loop. It's too far away for gravity keep turning it. The force gets so weak it can't cause enough acceleration to make it change its path enough to go in an ellipse. So the two objects become gravitationally disconnected from each other. And we call that escape velocity. So escape velocity is basically a tangential velocity. Well, it doesn't even have to be tangential, actually, but a velocity that's less than or equal to root 2 gm over r. So as the speed at which they become unbound from each other. Below escape velocity, the object will either orbit or fall to the planet. Uh, at escape velocity or higher, it will just leave and never come back. Gravity's still interacting between the two objects. There's no distance in which gravity stops working. It's just they won't fall back together. Now let's just talk about energy real quick. Okay, sorry, there's a lot to do here. So in a circular orbit, you notice that I'm changing direction, but I'm never going to change speed. So there's no work being done. So in a perfectly circular object, the kinetic energy and the gravitational potential energy remain constant the whole time. All right. But in an elliptical orbit, that's not going to be the case. So let's have an elliptical orbit like this. So in this case, the object is going faster than what it needs to orbit in a circular path. So what we find here is this, that in this case here, as this object moves in this direction here, so here's the velocity, the tangential velocity vector, here's the force vector, you can see that it's doing negative work. The gravitational force has a component that's going against the motion. So in this case, gravity is doing negative work, it's losing kinetic energy, but it's getting higher up, so it's gaining gravitational potential energy. At the farthest point, at the highest point, it will have its minimum kinetic energy, but it can't be zero, okay? And now, as it moves here, the gravitational force vector has a component that's acting in the direction of motion, so it's gaining kinetic energy and losing potential energy. And when I'm at these 2 points here, at the nearest and farthest, since gravity is acting at perpendicular to it, is doing no work at that moment. Okay, so as things go in elliptical, let's just think about this. At the near point, I'm traveling the fastest. I have the least amount of UG because I can't fall. You know, I'm as close as I'm going to get. So I've minimized my UG. But notice my ME is never going to change. There's no external work being done on this system. It is a closed system. So ME is going to stay the same, but we're just going to end up swapping as we do with a pendulum or whatever. We're going to end up swapping K for UG. So now if I get here, K gets smaller, UG gets bigger, ME stays the same. Now I get here, UG is maximized. I'm at my highest point. K is at its minimum. ME hasn't changed. Now, last thing we've got to talk about, and this is a weird one, so work with me here, and that is when we talk about potential energy, it turns out that we've said all along, and in most cases, if you're not dealing with an orbital system, College Board does specifically tell you to think in terms of what we call absolute potential energy. Well, we got this system here. You're just you get to define what you want to call the 0 point, right? So. If I had this object here, I'd say, oh, it's 1 to mg delta h. I'm going to say it's 1 meter. But the object here, now I'm going to say, oh, it's 2 meters. So it's got 20 joules of potential energy, whereas here it only had 10 because here it could fall twice as far. But if it was something on a pendulum swinging this way, I'd probably make this the 0 point. So I get to arbitrarily choose what to call 0 potential energy, right? We've been doing this, quite a bit this year. And that's usually going to be the appropriate approach to take. However, there is an absolute potential energy that an object can have. All right, and it's a little bit confusing. So work with me here. Okay. All right. So absolute UG is determined by finding the maximum energy that an object could have by lifting it a certain distance away from the planet. Okay. We seem to have lost something here. Okay. I apologize. I'll have to minimize this later. Okay. I'll make it fit so you can see it in the document here. But as the object is moving up, so let's just say from here, as I move it up, it gains, like if I'm close where the gravitational field strength is 10 newtons per kilogram, like it is here in this room, if I lift it up 1 meter, or 1 kilogram object 1 meter, it's going to gain 10 joules of potential energy. But what if I was farther away from Earth? I was far enough away that I only had basically 1/100th of that. Okay. So now what I find is I still have gravitational field strength, but it's just very weak. All right, and I lifted the same distance, but what I find then is that I gain a lot less energy for moving at the same distance. So as I get farther and farther from the other object, from the gravitationally strong object, I'm going to have less and less potential energy gain per unit of altitude gained. Okay, and then that gives us a diagram like this. So those who take, if you were to choose to do the AP Physics C test, this is probably one that you would get here. So what we find here is that if this is the distance between the two objects, and this is the force of gravity between them. So this is going to drop off as an inverse squared function with height. So I end up getting this, where it becomes asymptotic in these 2 points here. If I was to calculate the area under here, I would get a fixed amount, okay? And that would be the actual total potential energy the object could have. All right. So you can't. So the work it would take to take this object and move it basically to infinity is this much work. So therefore, that is the most potential energy it could have. Another way to think about this potential energy is if the object falls to the ground. Remember, it's giving up potential energy and converting kinetic energy. There's a maximum amount of kinetic energy an object can have by falling, right? And it's defined by the area under this curve here. So basically, we could think of it this way. So the absolute potential energy can be found by considering how much potential energy can be done by lifting an object away of object m away from object 2m. So remember, work equals force times distance, and then the force is the gravitational force, which I'm going to substitute in here, and the distance is lifted we're going to call r, how far it is between the objects. Okay. So now what I see here is that work ends up being just G big M little m over R. Now to find the absolute potential energy, we'll think of it this way. And listen, don't sweat it if this is weird. You can just memorize this, but let's just think about this. Okay, so we're going to use conservation of energy and say I start off with 0 kinetic energy, and now the object has this potential energy, the maximum it can have because we did work. At a distance of infinity, what we're going to say is it doesn't have any UG anymore, because if I move it, nothing happens. Like if I'm at basically infinite distance, if I lift it another meter, another 1,000 meters, it doesn't change its energy. So we're going to call that 0 here, and it doesn't have any kinetic energy. So then I end up getting this expression here, that UG plus work is equal to this. So if I want to solve for the UG using this for the work that was done, I get this negative value. So a lot of times kids, they don't like that negative value, but it does make sense. What we're saying is, let's call absolute potential energy is defined at being at a distance of infinity. At that point, you have 0 potential energy. That makes sense. Everything would have 0 at that point. If I get closer, therefore, I have negative potential energy. So this shows up on the test. Not often. There'll probably be like one question, usually an MCQ, where you need to know the absolute potential energy of an object can be defined as negative G mm over R rather than R squared, because it was the work expression. So the R and the cancel out one of the R squares. Okay, sorry that was a long one. I apologize for that. Hopefully I can figure out how to turn this off. Okay, thanks for watching.